take a moment to read through the information on page 144. Key information might be that there are squares cut from each corner. The original shape is a rectangle that measures 12 by 18 inches. You're going to bend the sides up to form a rectangular prism that has no top. And we're going to cut different sized squares and see what happens to the actual volume of the planter. We are going to start with a 0 by 0 inch square. Here's our original copper piece. If we cut off something that's 0 inches, that means we haven't actually cut anything off. So the height would be 0 because it's not a box. It's still just a flat piece of copper. The width will remain the 12 and the length the 18. The formula for volume is length times width times height. So multiplying these together, we get a volume of 0. And it should match our picture because a flat piece of copper has no volume. It doesn't have a third dimension. Now we're going to cut off a square that is 1 by 1 from each corner. So this picture shows it pretty nicely. The height of the box is the side length of the square, because these 4 pieces will be folded up, and so there's your height. This last piece will be the bottom of the box, so the height is 1. We had a side length of 12, but we are removing 1 here, so we are going to subtract that. We also are removing 1 here, so we're going to subtract another 1. 12 minus 1 minus 1 will leave us with 10 inches for the width. And if we did that same thing on the length, we're removing 1 on the left and 1 on the right. So 18 minus 1 will leave us with 16. And again, for volume, we're going to multiply those 3 dimensions together, and we will have 160 cubic inches. Now take a minute to fill in the rest of the table on your own. Hopefully you had these answers. We're going to look at the equation. So down at the bottom, you can see that they have an H, which means that they want more of an equation or an expression. So if you notice, you did just copy these values over. If we did that, the H would represent our height. As you were going down the list in the width column, you may have noticed that you're subtracting 2 as you move downward. It's an arithmetic sequence. You start with your 12 inches and you are subtracting 2 of those H values each time, 1 from the top, 1 from the bottom. And the same thing happens with this column. We start with 18 and we subtract 2 of those H values. The volume again is multiplying all of those together. We're going to use parentheses to show that all 3 dimensions are being multiplied together. We are going to take another look at the graph using Desmos. For this question, I'm going to move to the Desmos screen, but I just want to point out that they use function notation here. This means that volume is a function of height. So the height, the variable inside, this is the input. These would be like your X values. And the letter outside would be the output, usually like your Y values, what you get from inputting the height. So the volume is dependent on what you plug in for the height. And then we're going to look at changing the window using the values they gave us. We'll be describing key characteristics and then talking about the domain and the range. Here is our graph on Desmos. I have typed it in as a function. We have our v of h on the left, and on the right I just typed exactly what we had in the table. If you're going to use function notation, you want to make sure that the letter inside the parentheses always matches the variable that you're going to use on the other side of the equation. After we graphed, I went to this wrench here to change the settings. I typed in -10 and 15 because that's the window that they gave us for the x-axis. And then I went here and changed that to -400 and 400 so that our window is matching what they're asking us to look at. Let's talk about some key features of this graph. Here we have an x-intercept and a y-intercept because it is hitting the x and the y-axis. That is the point 0, 0. That would have been when we cut a square that had 0 by 0 side length, and we had a volume of 0. So that was the first row in our table. We have another x-intercept here, and this is 6, 0. In the table, when we cut off the 6 by 6 square, you could see that there was nothing left on the 12-inch side, so that's why we also had a volume of 0 there. Another point we want to focus on is this one right here. It's about 2.35, 228. So that, if we zoomed into just this region right there, that is a local or relative maximum. So at a height of 2.35, our box will have a volume of about 228. That will give us the largest volume box that we can make. The other thing that we want to talk about might be the other dimensions of the box. Back on the table, we said that the width was 12 minus 2h. We can just plug that h value in and we'll get the width of that box. The same thing can be done with the length. We said it was 18 minus 2h. If you plug in that 2.35 for h, you'll get the dimension for the length of that box that has the maximum volume. The last thing we want to talk about is the domain and range. So I believe this is question 2C and 2D. They ask you about the domain and range of the actual function. That would be the entire graph. So going on the left side, we are going farther to the left as we move down. So the domain on the left would be that we're going to the left forever. We're going to go to negative infinity. And on the right, you can see that we are going to the right as this arrow goes up. So we're going to positive infinity on the right. For the range, we are going up and down forever. And so the range would also be all real numbers or from negative infinity to positive infinity. So now for the domain and range of the actual problem. Well, we said that that first square was a 0 by 0, and that gave us a 0 volume. So that's the first possible point that we could have. And then as you saw, the volume went up, and then it started to come back down. And in the table, we saw that 6, 0, when we cut a square that was 6 by 6, gave us a volume of 0. And then you might have noticed that you had a -2 for the width and a negative volume. And we know we can't have a negative side length. So our picture really doesn't need any of this. Our problem is just this part of the graph. So we're going to write the domain and range for the problem, the real life restrictions that we have. So on the domain, we're again going from left to right. On the left, we started at 0. And on the right, we stopped at 6 because that's when we used up all of our copper. For the range, we're going in this direction vertically. And again, we could have a volume of 0. And that maximum volume we said was about 228, which came from that point right there. I just want to point out here is where you have that definition of the relative or local maximum. And they also showed you how you could get the intercepts. We've been talking about this, but if you set h equal to 0, you get this first root at x equals 0. If you set 12 minus 2h equal to 0, you would want to subtract 12 from both sides, which would give us a negative 2h. And then we'd want to divide by negative 2. 2 negatives would give us a positive 6. That's how you get that next root. And the same thing could be done with that last one. If we set 18 minus 2h equal to 0, we could subtract, divide, and get that positive 9. So it's the same idea that we have been talking about. You set each factor, each parenthesis, each thing that's being multiplied equal to 0 using that 0 product property, and then you solve for the variable. And then here, this is again where they just gave you a definition if you need it of a relative minimum. We didn't talk about any of those, but this would be where you have the least y value in a certain section or a certain window of the graph. And then lastly, this worked out example, we have talked about this before, but if you're looking for a particular volume, sometimes it's best just to graph a horizontal line and look for the points of intersection. So this would be one spot where they have a volume of 100. If you took that value and went down, you would get the x value, which is the height. You could also, if it was on Desmos, you could click on it and see the x value. Here is another point where you have a volume of 100, so that could be another height choice for the box. There's also another one here, but if you look, this is where we had said our real life scenario stopped. So this is not possible for our real life restrictions.